Well, hi. Well, my name is Julio Alcivar. This uh, this presentation for the autonomy work for 10. I have to talk about the concept called it automatic joint motion planning of 9 degree of freedom robot based on redundancy optimization for wheel hub polishing. Well, to begin with, it is important to understand what is the context in which this work was developed. This paper, this paper focused on the automation of automatic wheel hub polishing and an industrial process that has traditionally been carried out manually and present several problems. It is repetitive, physical demanding, generates metallic dust, and directly affects the operator health. With that advancement of intelligent manufacturing, industrial robots have become a very attractive alternative for this type of process, as they offer higher repeatedly, better surface quality, and improved safety. However, automating the polishing process is not trivial, especially when dealing with a complex surface such as wheel hubs. These were the main problem addressed by this paper. The main problem by the author is that the robotic system used has more degree of freedom than are actually required to perform the polishing task. In this case, the polishing task required 5 degrees of freedom, 3 for position and 2 for orientation. However, the complete system has 9 degrees of freedom. This leads to what is known as kinematic redundancy, meaning that there are infinitely many joint configurations that allow the robot to reach the same point, as we can see in the picture. Although this may seem like an advantage, in practice it's greatly complicated motion planning because the robot cannot automatically determine which of all of these configuration is the best. When properly managed, redundancy can lead to unnecessary movement, longer processing times, or even excessive mechanic stress. Well, the robotic system description, in this case, uh, to try to solve this problem, the authors design a system composed of three main elements. Well, the first element is a six serial robot industrial, which provide a wide range of motion and position capability. The second element is three-axis polishing atom and mount at the end of the robot, whose function is to finely adjust the position and orientation of the polishing tool. Finally, a positioner is included to rotate the wheel hub during the process. The combination of the robot and the actuator results in a 9 degree of freedom system, which is highly flexible but also highly redundant. What is, in this case, the redundancy is a problem? Well, in a non-redundant system, for each point along the trajectory, there is a unique inverse kinematic solution. But in this case, for each point on the wheel hub, there are multiple possible solutions, and not all of them are equally good. Some solution may generate abrupt movement, others may bring the robot close to singular configuration, and others may simply increase the total polishing time. Therefore, the challenge is not only to reach the point, but to reach in the best possible way, considering time, efficiency, smoothness, and physical constraints. What is the general methodology? Well, the methodology proposed in this work is clearly divided into two main stages. The first stage is the offline program. The offline programming, which is responsible for generating the polishing trajectories based on the CAD model of the wheel hub. The second stage is kinematic redundancy optimization, where the motion of the robot joints is determined in order to follow the trajectory in the most efficient way. This, this separation is essential because it allows the geometry problem to the club from the dynamic problem. In the offline programming stage, the author worked directly with the CAD model of the wheelhouse. First, they divide the surface of the hub into two radiant simple areas, where redundancy optimization is not required, and the compensators such as hub holes, where the robot motion is much more demanding. In this complex region, these red points are generated that includes not only the position but also the orientation of the tools. Each of these points represents a pose that the robot must follow during the pollution process. Point reduction using a new version of Doolan's Picker algorithm. An immediate issue with this approach is that if too many points are generated, the subconscious computation becomes very costly. To address this, the author proposed an improvement version of the Douglas Picker algorithm. Unlike the classic algorithm, which only considered the distance between points, this version also takes into the account change in tool orientation. This is fundamental in polishing application, because even a small variation in posture can cause collision or surface defect. Once optimized points are attained, the most important stage of the work begins. Here, a redundant space is defined using three-axis position actually. For each point along the trajectory, multiple possible combination of the three axes are evaluated, and for each combination is calculated. Well, to solve this optimization problem, the authors combine two algorithms. The first is a sign causing algorithm, and the second one is the greedy best first search, which prioritize solutions that provide shorter processing times. The combination of both algorithms allows solutions close to global optimum to be found with much lower computational costs than other methods. This is crucial for making the algorithm be able in real industrial application. For the results of the paper, while the author did not evaluate the method quality, but rather the very clear metric. And one of the main metrics is total processing time. Well, in this case, it is because first the pollution trajectory is generated on one of the internal surface of the wheelhead special coloration. It is the most complex. For this reason, improved dual speaker algorithm is applied, reducing the number of points while considering both tool position. The results of the results show that the ACI GBF methods reduce polishing time from approximately 9.4 seconds to around 5.8 seconds, while maintaining smooth joint trajectory. Most important, most important, these results achieved is much lower computational time than other more complex methods. Thank you.